As we proceed into a different unit, now we're looking at two new types of functions, exponential and then eventually logarithmic functions. And because we are starting to shift into these new functions, we need to look at what their graphs look like. And so our essential question for today is how do we graph the transformation, and specifically transformations, because there's more than one, of an exponential function. Two objectives: yes, I want to graph any exponential function that I'm given, but I also want to model with them. These are not traditional word problems. We're kind of using just our normal formulas that we've been given before. And let's start with a definition. And exponentials are set up like this. And if I have anything where the variable is going to be in the exponent spot, that's going to give me my exponential. And specifically, my definition is f of x equals a to the x is an exponential function with base a, with a greater than 0, so it has to be positive, and a not equal to 1 because 1 to any power is just going to be 1. If we look at a few different types, and what I would say is plug those into your calculator. So on 1 through 5, you can plug them into your calculator. You're going to see that 1 and 2, the graph gets very big very quickly. And so these two functions have a general shape that looks like this, where it hugs that x-intercept or x-axis, but then it increases very quickly. And we call these exponential growth. In number 1, things are doubling. In number 2, things are being multiplied by 10 each time. 3 and 4, you can see the fractions there. Those are exponential decay because things are getting smaller. And so this example would be exponential decay. Again, it hugs the x-axis, but it drops as you go to the right. And again, these are exponential decay. And if you look at our definition for decay, you notice that your b value or your base is between 0 and 1. That's why 1/2, 1/10. It's between that range. So when I raise it to a power, values get smaller. On the other side, if it's bigger than 1, things get very large very quickly. And last but not least, the new piece for today, and it's not really new, this is an exponential growth model as well. And it's an exponential growth model because e is 2.718 roughly. It's an approximation. Kind of like pi, e is a number that we are going to use consistently. Because I will ask about domain, range, x-intercept, y-intercepts, all of those things, we do need to start with some general properties, and they're listed there. Domain is going to be a set of all real numbers. That's important. So any exponential function that you have, the domain will always be all reals. If there are no transformations, your range starts at 0 to infinity and then goes to infinity, and notice that it is open at 0. That's because it's never going to intersect that axis if there are no transformations. It talks about it when it's increasing or decreasing, and then also the y-intercept and what the asymptote is. And in an exponential function, you're always going to have a vertical or a horizontal asymptote. So that's the difference between exponential and logarithmic when we get there. It's going to be a horizontal versus a vertical asymptote. So important pieces here, because this is going to be contrasted with what we do with logarithms. Domain is going to be all reals. Range is 0 to infinity. And the x-axis is the horizontal asymptote. And sometimes for me, it's easier to write instead of the x-axis, how about y equals 0? And you can see that there is a relationship between the number of the horizontal asymptote, 0, and where the range starts. Okay, so transformations and kind of what they do. As we're looking at this, this represents a horizontal shift. This represents a vertical shift. And A is going to be your stretch, shrink, all that information. And for this one, I'm going to ignore it for just a moment. So looking at what we have down here, and we are going to graph each one of these. Okay, so I want to start with my parent function, which is f of x equals 2 to the x. And you can see that every single one of those has a base of 2. So if there's no transformations, we just start with 2 to the x. And in case you're not comfortable with it, I'm going to draw just a quick sketch by plugging in numbers. If I plug in 0, I get 1. So 2 to the 0 is 1. 2 to the first power is 2. 2 squared is 4, and maybe one more. 2 cubed is 8. And so we get a general picture that looks like this. So 0, 1, 1, 2, and 2, 3, 4. And 8 is somewhere up there. Okay, and so those are the 3 points that I'm going to be moving around. When we look at number 1, I want to talk about the transformations first. So the horizontal shifts, it's always going to be the opposite of whatever sign you're given. So the x plus 1 in the numerator is going to shift it left 1. Okay. And then I'm going to start looking at what my domain is. From the first page, and I'm going to be referencing this a lot. So you might want to flip back and forth. So looking at that, my domain is always going to be all reals. Range. On the previous page, my range was 0 to infinity. If I shift a graph left, that doesn't affect range because the range is y values. It's only affected if I move up or down. So my range stays the exact same, 0 to infinity. And the asymptote that goes with it is y equals 0. Again, if it's y equals 0, that's a horizontal line. Shifting a horizontal line left 1 doesn't do anything. And so I would take all 3 of those points and shift them left 1. Left 1, and left 1. And my new graph looks like this. I'm mainly looking for those 3 points, so it doesn't have to be a perfect graph. Number 2. There are 2 things going on here. It's going to be a shift right 3 and up 1. Domain remains unchanged. My domain is all real numbers. Range is not affected by the right 3, but it is affected by the up 1. So it shifts that 0 to infinity on the previous page. It shifts it up 1 spot, and so it becomes 1 to infinity. And then the asymptote, I'm going to abbreviate that differently. Let's just go HA, is going to be y equals 1 as well. Just to reiterate, these numbers are always going to repeat, and that's because they're affected by my vertical shift. And then last but not least, I want to graph what's going on. So I'm going to shift my black points right 3 up 1. So I'm going to go 1, 2, 3, up 1, 1, 2, 3, up 1, 1, 2, 3, up 1, and I get this general shape again. And something like that. Okay, last but not least, we have a reflection, and it's over the x-axis. A reflection over the y-axis would look like this, not like that, 2 to the negative x. So that would be a y-axis reflection. What that does, it does nothing to our domain. It's all reals. It does affect our range and our HA though. And so if I start at 0 to infinity on the previous page, that's what every parent function starts with. If I flip that over the x-axis, it now goes from negative infinity to 0. And then if I shift it down 2, I shift it from 0 to negative 2. So my range here is negative infinity to negative 2. My asymptote follows that, and I shift my original asymptote down 2 spots, so y equals negative 2. And so now we go through this process. So I'm going to start at that point 0, 1, flip it over the x-axis, and then shift down 2 spots. Reflect over the x-axis, shift down 2 spots. Reflect over the x-axis, shift down 2 spots. We get a general shape that looks like this, where it approaches y equals 2 but doesn't quite cross it. And so I'm not very picky, but I do want to point out that there is a horizontal asymptote that goes through y equals 2, and so it never touches that purple line. So the only way you can really be dinged points is if I do not see the 3 points that you're moving, and if your graph crosses the asymptote that you set up. Last but not least, and I'm not going to spend a whole lot of time going through these problems, and truth be told, we're just going to do them tomorrow. But here's how compound interest works. We have two different formulas that we're going to utilize. We put money into an account, interest is compounded, and the interest is added to the original, and then it's kind of like rinse and repeat, where more money builds on itself, and it gets very big very quickly, or at least that's the goal. Letters that it stands for: A is always the amount you end up with, the final amount. P, it's abbreviated P because it stands for the principal, that's the original amount that you put in. T is always the time in years. When you talk about your compound interest formula, it's always dedicated to years. And then last but not least, R is annual interest, represented as a decimal. One more abbreviation is N. N is the number of times it's compounded. If it says annually, that means N equals 1. If it says biannually, that means 2. If it says, or biannually or semi-annually, it's the same thing. Monthly is 12, quarterly is 4 times a year, and daily is 365. And truth be told, depending on what type of loan or account you have, sometimes it's represented as 365.25 to either squeeze an extra little dollar or two out of you or to prevent you from making that dollar, but it just kind of depends on the situation. For us, we're going to use 365. So the two formulas that you're going to have are your compounded n times a year, represented by this formula, and compounded continuously, represented by this formula. That's the PERT. Now, a few things. Yes, we're going to have to apply what we know, but at the same time, these formulas will always be given to you on this test. You do not have to memorize them. So just make sure that you can utilize them well. And then a couple extra things that I want to right off the side. If I talk about population growth, generally it's set up like this: A equals P times 1 plus R all to the T. And I should be a little bit more, I'm going to say, let's call this a general growth. I shouldn't call it population growth because that's not exactly what it is. And if it's a general decay, A equals P times 1 minus R all to the T. What you will use this for me is called depreciation. And this will help you on quiz 1. Just something to reference for later on. For tomorrow, or actually today, that's what I'm looking at for the homework, and we will continue the discussion in class.